So, good afternoon, everyone. Today, the Atoms Seminar has the great pleasure to welcome once more Professor Richard Elliott. I think by this time he needs no introduction. He is a great friend of the Atoms group, and he has been with us since the beginning of this seminar series. He's currently a professor emeritus at the Chemical, Biomolecular, and Corrosion Engineering program at University of Akron. And as I'm basically welcoming him home, I'm gonna leave you all with him. So thank you so much, Professor Elliott. And please feel free to share your screen and start your presentation.
Let's see, is it sharing or no? Oh, now it's sharing. Okay, got it. And, oh, what happened? Oh, I got to minimize this. All right, let's try it like that. So thank you again for letting me visit with you guys. It's always a pleasure. And today I'd like to talk about something a little different from the previous lectures. Maybe when we first started, we started with some practical considerations about equations of state and artifacts and that sort of thing. Well, and then we did a lot of statistical mechanics, and then now we're going to bring it back and talk about more practical things again in the context of this project that I'm working on with co-authors called The Properties of Gases and Liquids, the 6th edition. So the basic idea is we all love our statistical mechanics, but at sometimes you have to give a general checkup of how the latest theories and the latest data and compare with the old theories and the more established theories and see, are we making progress? So that's really what this project is about. And I think I've probably shown you some version of this slide before. That this project actually is a big part of the reason that I have the emeritus name in my title these days. It's a lot of work. It's a labor of love to really put these latest theories to the test and compare everything on an equal platform and see how things are doing. So this is our mission statement. We want to survey basically all of physical property methods, estimation methods, and compare them to all of the existing data. So that's the goal, and we just have to get some approximation of that with the 6th edition, and the 7th edition will get a little closer to that. And then the rationale is that we'll make all of our current applications reliable, and future progress in the field will be advanced. So something we're doing a little bit stronger emphasis in this edition is we've enlarged the databases by bringing in representatives, co-authors from National Institute of Standards and Technology and from the AICHE DIPPER compilation project. DIPPER focuses mainly on pure compound properties, has about 2,300 compounds in there. Their mission is to dig deep for those few compounds that have been established by their industrial advisory committee to be on their list, and for whatever properties the committee has established need to be represented, they will get the best estimates of those properties for every compound in the database. And so sometimes that means they have to estimate, and sometimes they need to collect all the best data. So that's a focus though on pure compounds. And the National Institute of Standards and Technology, the TRC, Thermodynamics Research Center, their mission is a little broader, is to collect all the data in the world. Pure compounds, mixtures, whatever it is, but they have a little twist to their mission. They want all of their data in their database to be traceable to the original literature reference. No estimations, no smoothing. sometimes, it's not a perfect world, but their objective is only the raw data. And so you can see how they're different missions, and with such a broad mission, the NIST TRC project can't go as deep sometimes in finding all the properties. And here's one example: is the Dipper project will accept measured properties from members of their committee that have not necessarily been published in the open literature and reviewed, whereas the NIST would not accept that. And so that's just an example of some of the dichotomies between these two databases. But by bringing them together, and as often as possible, reconciling the differences, we hope to get the best of both worlds, and that's my objective, at least within the context of this PGL. I'm going to just refer to it, PGL effort evaluation. So that's enough, I think, about that one-liner. Well, before you fall asleep, let me just say what we found out so far. We're basically through the vapor-liquid Equilibria chapter, and I have some preliminary results on transport properties that I'll just hint at, basically. What we're finding is that the fundamental methods with the statistical mechanics and quantum mechanics are proving to be competitive with traditional methods like group contribution methods, especially for properties like heat of formation and vapor pressure. When it comes to mixtures, this Cosmo-RS method, which has a quantum mechanical component to it, is competitive, I would say, with UNIFAC. And this Huron-Vidal mixing rule, that's density dependent, basically applied to the equation of state instead of just the activity coefficient, is pretty competitive now with UNIQUAC. What that means is you don't need to have activity models with a separate model for an equation of state. And then this SpeedMD method, which is a kind of a cross between a group contribution method and an MD method. The reference fluid is fully simulated, and the attractive interactions are inferred by a kind of regression. Well, it's close to being competitive to this Huron-Vidal method. So that's pretty much where we're at. Those are the highlights, and so now let's dig into some of the details. A couple of weeks ago, Carlos Vega made a presentation when he said, well, physicists think that everything is already well known, there's nothing new, and so they're moving on and they're doing things with quantum-based superconductors or those kinds of things. And that's a nice thought, but what we know is that for engineers, it doesn't always work out that way, that we can just plug in the Schrodinger equation and get the properties that we need. And I was impressed by the thought that Carlos had expressed, because I had just read that paragraph in the first edition of the Properties of Gases and Liquids, which was written in 1958. And this paragraph, in almost identical form, is still the first paragraph, and it will be the first paragraph in the 6th edition too. And so it's a wonderful thought, but it's been around for a while. And around about Y2K, the year 2000, there were a lot of people who were saying, computers have come so far, this is it. By the year 2020, all of those old-fashioned methods will be absolutely obsolete. And so a lot of people started investing in that technology in Y2K. And then they said, well, you know what? It's not working that well. We're going back to our old methods. And the joke became, well, that modern physics approach is the technology of the future, sure, but it always will be. In other words, that future will never come. And so that was just a kind of a sad joke. And to me, being one, who really loves the statistical mechanics, that really hurt me bad. And so I doubled down and I said, well, we're going to keep trying. The good news is here in 2021, we are getting closer. And so I'm going to try and show you results that for vapor pressure and preliminary results for transport properties, I think it's pretty clear that the transferable force fields are superior for predictions of those properties. For the ideal gas properties, pretty demonstrable that the quantum mechanical methods are superior to any kind of group contribution method. And I guess I said this before, but the Cosmo RS type methods are competitive. I can't say that they're better, but they're pretty close. So let's talk about the sample results. And these are the properties that I'll be talking about in detail. And then I'll show you some preliminary results for these properties. So when it comes to predicting a boiling temperature, there aren't a lot of force fields out there that have really tried this. And so the only one I felt like I could go with there, that they had tabulated their predicted values of the boiling temperature, was the trap UA method by Seepman and co-workers. And so there aren't a lot of compounds there to compare to when you look at how much the group contribution methods can do. And this is a case where it was early on and we had time, and so we put a big effort into combining the databases of NIST and DIPPER. And so we've got about 4,000 compounds represented here with boiling temperatures. So the general trend that you see is that they're all pretty similar. There is a method that actually I worked on. Oh, I forgot to put the reference. Oh, here it is, Imami. Okay, so Imami et al. Is around 2004. What we were trying to do in that paper was make the point that the critical temperature of long chain molecules is known not to go to infinity. So the way you can get some idea of this is plot 1 over the critical temperature versus 1 over the molecular weight. And what you see is the intercept of that curve is not 0. And so there's a finite value for the upper limit of the critical temperature. How can that be? It seems very surprising. But if you think about it, if you've got a spaghetti of long chain molecules and you're trying to make it boil, if one loop of that long chain has enough energy to sort of pop out of the soup, once that segment is free, to pull the next segment behind it is kind of like unraveling a string in a piece of in a sweater, right? Once that one is loose, the next one just follows through it. It's called reptation. And so that physical phenomenon is why if you can just make one segment boil, then the whole rest of the molecule will come unzipped and it will boil. And so that's a rationale for why there's a kind of a finite limit to the critical temperature. And this has been measured experimentally, and it goes back to work by Sinopoulos and many co-workers back in the 70s or 80s. So we wanted to make that point, so we reformulated our group contribution method to make that be true. Well, surprising to me, it actually worked out even better than the other existing group contribution methods, even for molecules that are not heavy. I guess I should have mentioned, what is a heavy molecule? Hexadecane and anything heavier than hexadecane is a heavy molecule in our classification scheme. Polar means it doesn't have any kind of hydrogen bonding, but it's got like nitrate or something like that, or an ester. And normal is anything that's not those things. So let's now take a look at the ideal gas properties. Now, there's a method being developed by the TRC group at NIST, and they call it this LCC method. And it stands for a local coupled cluster method. What they've tried to do is formulate their method to get a happy medium in between the most sophisticated basis set and the highest number of conformers. So when you start having to deal with so many conformers, then you can't afford to do the ultimate basis set. And so what's a reasonable trade-off? And they came up with a way of their way of doing it. Okay, and so it's a paper by Polechka and Kazakov, and so I recommend it to you because it really stands out. At one level, it's easy enough to say, well, okay, a quantum mechanical method is going to do better than a group contribution method. Maybe some people would say, oh, we've known that for years. But it's not just any quantum mechanical method that does that much better. And so you can see that this LCC method is significantly better than another method that's also based on a local coupled cluster, but it's got a higher basis set. So even though it's got a higher basis set and it's much slower, they haven't optimized their trade-offs in the best possible way, because the LCC method of the TRC is demonstrably better in all but one class of molecules, and in that case, it's just about the same. Okay. So and this other method, because it has such large basis sets, they don't have as many compounds. If you compare the 90 to the 880 or 800, that's almost a factor of 10 improvement over the best existing methods. So I think that's pretty much of a slam dunk. But you could ask, since the databases that are available, different group contribution methods can't represent all the different molecules. The database that Polechka and Kazakov developed, they did just 2,500 compounds that were limited to H, C, N, and O. Recently, they've done 34 fluorinated compounds and 87 sulfur compounds. Those will be published next month. They are not included in this analysis. Those data sets came out too late for us to include. But what they've shown is very similar kind of a trend. So what if we put all methods on the same exact basis of all compounds? Again, the trend is pretty much the same, but not quite as dramatic across the board. When it comes to the absolute entropy, this is what you need to be able to predict the Gibbs free energy, which is necessary to predict your reaction equilibria. It's a similar story. In this case, it's maybe 5 or 6 times better. And this QM method here is the LCC method. If you reduce the data set so that there's just the exact same number of compounds in each data set, let's call it a factor of 3 improvement. Again, not a slam dunk, but I think it's good enough to say that the group contribution methods are, why would you use them? And heat capacity and entropy are very closely related. And so it's no surprise that it's a factor of 3 for these two. The surprise for this property to me was that there's so few compounds that have actually experimentally measured heat capacities. It's like, what is that, 150? So now let's take a look at vapor pressure. And so this is a property that's near and dear to my heart. I've done a lot of work on this property. I always felt it was important because VLE is so important for engineering, vapor-liquid equilibria. And you can't get the vapor-liquid equilibria of the mixture right unless you get the vapor-liquid equilibria of the pure fluid right first. And so the vapor pressure is essentially the VLE of the pure fluid. So some highlights in this slightly large table. RefProp, I think, is probably familiar to everybody. This is the product that TRC puts out. If you go to the chemistry web book, the fluid properties that they post are being derived from some edition of the RefProp. Usually the ones that are on the chemistry web book are like 5 versions previous to the latest version. We're using the latest version, and it has about 150 to 180 compounds in it that they've characterized with very multi-parameter equations of state. So their goal with those equations is to use however many parameters they need to get an equation that represents the data to within the uncertainty in the data. So this is a kind of a gold standard, but they don't have as many compounds represented. So if we see that the overall standard is like 1%, and you've got another method that's 1.4 that's not using 40 parameters per compound, you got to give a little bit of credit. I think if you've got 2 parameters instead of 40, and you've still got 1.4% versus 0.9, I think that's pretty good. And so that's represented by this method that I'm referring to as the Joubert method. It's a volume translated Ping-Robinson method with a custom fit to this alpha parameter that characterizes the temperature dependence of the attraction. And what they did was they tuned those alpha parameters, and it has like 2 or 3 parameters per compound, and they fit each one of those 3 parameters to the data in the DIPR database, which is the exact same data as what we're comparing to. So it's not a huge surprise that they're doing this well. And so that's the nature of the comparison. The PC SAFT equation, they did not have the DIPR database, but they tuned it to available data in the literature that they could find. And they're doing pretty well. The SpeedMD method, what I'm calling the SpeedMD method here, is a custom fit, non-transferable version of the SpeedMD method. And so let me explain what that is. If we take the first order perturbation term that we derive from the transferable force field, and we just multiply it by something that I'm going to call KII. So that's not KIJ, this is KII. So this is some fudge factor for the interaction of the molecule with itself. It says every molecule has its own specific character that doesn't necessarily transfer from molecule to molecule. And this is the correction for that non-transferability. And if we just correct the A1 term with 1 parameter for that attraction term, and we correct the van der Waals volume term from the transferable force field with 1 parameter, then we get this SpeedMD method. And the database that we use to fit that is pretty close. The DIPR database evolves over years, and we used a version from 15 years ago. So that's the basis for our correlation. I colored this red not because that's a bad thing, but because it's basically 2.2 and 2.2 for PC SAFT and SpeedMD. But because I wanted you to look at some of these other red items that I want to compare to. Before we get to that, let's just compare the yellow highlighted items. And so this is the transferable version of SpeedMD. And what you see is there's not as many compounds in the database. Why is that? Because water is not a transferable compound. Methanol is not transferable. So there are a lot of compounds, nitrogen, oxygen, argon. These are not transferable compounds. And so the database is smaller when you're talking about transferable compounds. That's a distinction. And because you're using a single force field for everything, you're going to expect to have some larger deviations. And that's what we see. We see about a 12% deviation when we develop this force field that's transferable for all the different types of molecules. So in the case of SpeedMD, the difference of going from a pure transferable predictive mode for vapor pressure down to a custom fit is a factor of about 6. And so you get that much of an improvement. Well, how do we compare that to existing methods of group contributions? Well, I took this, so the EMB method that I talked about for boiling temperature can also be adapted to predict the shape parameter and the epsilon parameter and the size parameter of the ESD equation of state. And we can also do the thing with same thing with PC Saft, but the errors were larger, so I didn't fit them into this table. Okay, and so let's think of this ESD group contribution method. We're just taking the molecular structure and predicting all of the properties, including the vapor pressure, from that equation of state, and we get about 32% deviation. Well, okay, maybe you think that's not the same as a traditional method. There is a traditional method, a unifact method for predicting vapor pressure. I didn't include it here because we evaluated it when we developed this group contribution ESD method. That method is around 80% deviation. And so we're just kind of discarding that one. This is the one then that gives us about 32% deviation based purely on molecular structure. Well, what if we had one vapor pressure point? And the most commonly available vapor pressure point is the boiling temperature. Let's take that experimental boiling temperature, predict the other properties of the equation of state from the group contribution, but refine the epsilon parameter of the equation of state to fit one boiling temperature. And so you can see that that gives us almost a factor of 6 reduction in the deviations of the vapor pressure. So it's extremely valuable to have one vapor pressure point. And this then gives you some sense then of what we can do. And I've looked at other force fields, like the trap force field gives you about 40% deviation in vapor pressure. The Potthoff force field, this Me force field, is doing much better, but it's on a much more limited number of compounds, mainly just hydrocarbons right now. But it's still right around 12%, 11 or 12% deviation. And that sort of confluence of the different methods leads me to believe that 12% is probably about as good as we're going to do with a transferable force field. Let's talk about mixtures. When it comes to the excess volume, we can compare all the different methods, and now we have a breakdown according to many different types of molecule-molecule interactions. So if it's associating molecule with an associating molecule, if that's the binary mixture, then that's this column. Associated heavy, associated normal, associated polar, and I think you get the idea. So we would probably expect to see the largest deviations when you put an associated molecule with a non-associating or normal type molecule. And we do, but it's not always that way. So they're not hugely different. And when it comes to PCSAF, it's very similar actually. The Joubert method, which is based on a Ping-Robinson method, doesn't do so well when it comes to the heavy molecules usually. And so you see this number here and this number here, they tend to be somewhat larger for this volume property. So that's not unexpected, and that's the trend that we might expect to see. When it comes to the overall predictions, I would say that the ESD 96 and this PSRK method, which is more of a predictive method, they are maybe stand out in a negative way. And then RefProp tells you that, okay, yeah, we've got 100% error here. That sounds like a lot, but remember, these are deviations, very small deviations of the excess volume relative to the actual volume. And so it's 100% of a very, very small number. So the point of including this RefProp number in the green is to say that if that's the gold standard, then 135 versus 120 is not that different. And so these more or less predictive methods, because they weren't really, this wasn't a targeted property in the parameterization of those methods. So these methods are doing about the same. What about the heat of mixing, the excess enthalpy? Then we have this breakdown, and what we see is that the group contribution methods now are standing out. They're about half as much deviations in excess enthalpy as the equation of state methods. Some of the equations of state are a little bit better, and the surprise to me was that the ESD method, and I put the 96 on here. What that refers to is there was a paper in 1996 where we developed a very simplified treatment of the association terms and showed that you can factor the association terms and solve the impact of association very, very efficiently. And so this is using that efficient factorization method. The SpeedMD method is using the full-on Wertheim treatment. So for a molecule like ethoxyethanol mixed with water, you've got to worry about the solvation between the ethoxy ether with the water separately from the ethoxy hydroxyl with the water. And there's a lot of complex interactions that lead to a very large nonlinear matrix of interactions that you have to solve for. This method doesn't it just basically treats ethoxyethanol as ethanol with an extra tail on it. It ignores the ether part. So it's kind of surprising to see that it arguably it's at least equal. So that was a little bit of a surprise. So let's get to phase equilibria. This is one that is really important in the chemical industry. Here we've used it. I'm going to talk about two databases. One is a recently published 2020 vapor liquid equilibrium database. So why didn't we just use a TRC database? Why would we use one that is open to everybody? Well, it's new enough that, in my judgment, people haven't used it as a training set yet, not specifically. And so, at least not everybody. I think Joubert has. So another motivation is it's a lot of work to go through and curate the data and extract a database that doesn't have any weird flukes to it, is traceable with complete provenance to all of the references, and has a minimal of smooth data. And so it's a lot of work. And they had done that work. It was going to be a lot of work for us to do on our own. And then because NIST has to put in so much work to gather all of this data and curate it. They have to be a little careful about just giving all of that away. And so they have to, I won't say protect it, but you have to go through a much more elaborate procedure before they can just put all of the data out there. Whereas Joubert had already done this for us. And so we decided just to go with the Joubert database. And so you can see that it's about, it's 203 binary mixtures in the database. Because of convergence issues, different methods didn't converge for all of the binary systems. But pretty well represented. And you can see that the refprop method here, again, is the gold standard, but they're cherry picking in terms of which compounds they're representing. And so that's a tough comparison, but this gives you some sense of, you know, if you're doing it that well, then you're doing pretty well. And what we can see is this PR Lorraine, which is the same method as the translated consistent Ping Robinson that I talked about with the vapor pressures. So it's the same equation of state for the pure fluid, but I wanted to consider and compare both quadratic mixing rules for that equation of state, the traditional quadratic mixing rules, and their Huron-Vidal local composition mixing rules. And so I had to give two names to this same equation of state for pure fluids. And you can see for non-aqueous systems, not too much of a difference. I would say that this PR Lorraine method, because it's getting the vapor pressures right, the DLE of the pure fluid right, has an advantage. When you compare to the SpeedMD method, though, this is the custom fit SpeedMD method, not the transferable one. It's close, I would say. And considering that the SpeedMD method has one parameter per binary mixture, whereas the PR Lorraine method has two binary parameters. And so if you bring into account, you know, the difference in the number of parameters, I think it's fair to say, well, these are not that different, really. The difference between these systems is the aqueous systems they stand out as being much more difficult to represent. And within the aqueous systems, of course, methanol water is not difficult to represent. And so it's really got to do more with the gases mixed with the water and the hydrocarbons mixed with the water. And so those systems are showing some large deviations. And this is an opportunity for advancement before the next edition of properties of gases and liquids. So that database of Joubert covers low pressures and high pressures. There's an older database by Danner and Guess that just focuses on the low pressures that are maybe more interesting for the activity models and more applicable for the activity models like NRTL and UNIQUAC and the methods that you're probably used to hearing about in applications of process simulators. And what we see is, and the reason I put this in red is this evaluation is not done yet. We're still getting more systems into the database and more parameters characterized. And so we're not completely done, but I don't think the trend is going to change very much. What you see is you get about 1% error when you've got two parameters per binary system. And at low pressure, the PR Lorraine method has that. And so it gets about 1% deviation. And that's even for the entire database at these lower pressures. The equations of state with one binary mixture, the old 1976 Ping Robinson equation state, I think you could say, is obsolete relative to quadratic mixing rules with the updated version. So it's not just the mixing rules here, it's the improvement in the vapor pressure characterization. And it's about 3%. when you talk about equations of state with one parameter per binary mixture. I wanted to spend a little time talking about understanding the activity models. If you look at the activity coefficient at a constant pressure, you see that there are three components. If you want to decompose the activity coefficient into its different components, you've got to apply the expansion rule and make sure that you've got each component identified individually. So that's a little bit of a trick there to be aware of. But once you've done that, at constant pressure, what you see is that the repulsive part is going in one direction, the attractive part is going in another direction, and then the association part is going in another direction. And this is the packing fraction. You see the packing fraction is going down as we go to the larger molecule. Well, if you do the comparison at constant packing fraction, you get something very interesting. And that is the repulsive part, the repulsive contribution to the activity coefficient is actually 100% exactly 0. So where does this athermal term come from? Where it comes from is the log of z term in the fugacity coefficient that is actually the correction to go from a constant volume equation of state to a constant pressure property of activity coefficient. So in a short form, the Flory-Huggins athermal term actually comes from the ideal gas reference, not from the repulsive contribution. So that's the main point I wanted to make today. If I had more time, I would talk about local cluster quasi-chemical theory. And I saw Dilip Astigiri is in the audience. He and Lawrence Pratt worked together around Y2K to reformulate quasi-chemical theory so that it is in a more modern off-lattice context and can be adapted more generally. I'm still working my way through those papers, but the quasi-chemical theory then that lays the foundation for Uniquac and the Wilson model has the capability to be updated in a more modern context. And so that's something that I look forward to seeing more of and maybe a more rigorous evaluation of in the 7th edition. I did some work on second virial coefficients recently, and I've talked about this just briefly in the past, and I showed you this algorithm. I wrote it up recently, and I included some Fortran 90 code for doing this on-the-fly method. Basically, what it involves is choose any configuration with 1,000 molecules. You get a large number of orientational samples and actually a sufficient number of conformational samples that you can just take any configuration that's been equilibrated and calculate your second virial coefficient from that. It takes about 5 minutes, and it gives you a lot of insight into these molecular interactions. It's also a very good educational exercise because you're just looking at how two molecules interact, and if you understand, what is the force field between those molecules, you can calculate this quantity. It's very, very, very easy. So how are we doing when we compare to experimental data? It turns out it makes a huge difference which force field you use, because the force field is very closely tied to the vapor pressure behavior through these equations. And so what we see is the Potthoff force field, which uses the Me potential, is doing a much better job for vapor pressure and a much better job for the second virial coefficient. Second virial coefficient is another one of those properties that there aren't as many of those experimentally characterized as you might think. And so we don't have enough data yet to say, because there just aren't enough force fields that have been characterized yet to make a definitive statement about second virial coefficients, but it's encouraging. Preliminary results are encouraging about being able to predict second virial coefficients from force fields. Well, one of the things you get from that on-the-fly virial coefficient method is you get the perturbative virial coefficient. So you can break down the force field into its repulsive and attractive part and evaluate them separately. That comes in handy in a second because, well, what we've done here is we've predicted viscosities using the force field that was characterized based on vapor pressure. And the two of these here are the Potthoff force field and the trap force field. And so what you see is the trap force field, which does much worse for vapor pressure, also does much worse for viscosity. And so these are predictions, pure predictions of viscosity from the Potthoff force field because viscosity was not included as a property in the characterization of that force field. And it's true as we go from to longer chains. I didn't have room to include branch chains, but if you read the paper, those are done. The trends are very good there too. And when we extrapolate to extremely high pressures, these kinds of pressures are interesting in tribology applications for lubrications of ball bearings. So these aren't ridiculous pressures actually. And so it's amazing the extent to which the extrapolation is valid. Coming back to the importance of the separability of the second virial coefficient. I've shown you this slide before. If we want to optimize our force fields and get predictions of transport properties too, then we can use the EMB method to expedite the simulations, and the resimulation just takes 4 minutes instead of 4 hours of the original simulation. Well, we know how to do the integration of the Helmholtz energy from the compressibility factor. We know more about that than a piecewise quadratic polynomial. We know it has some sort of a functional form like this. And when you have the components of the second virial coefficient, you only have very few parameters left to infer on the isotherm and then on each one of these isocores. And so with this approach, we should be able to characterize the entire vapor pressure curve for each individual compound with just 8 state points. The beauty of that is we can now do 4 compounds simultaneously on 32 CPUs. If you want to have a transferable force field, you have to optimize multiple molecules simultaneously. That's the whole point of it being transferable, is that it applies to multiple molecules simultaneously. So you've got to optimize that force field simultaneously. The only way to really do that is to have multiple molecules in your database that you're optimizing all at once. This approach is going to make that much more feasible. When it comes to self-diffusivity, the reference is on the next slide. And the point I'm trying to make here is that if you do the molecular simulations in this frame of reference, extrapolate to the intercept, and you look at that low density intercept, there's a question of whether that behavior is like Chapman-Inskog, which is hard sphere behavior, or is it Rouse scaling, which is what polymers should do. Well, we know that at high density, it follows Rouse scaling. Everybody has always assumed it must follow Inskog even for long chains at low density. But if we look at this low density intercept, we see that for small molecules, you might be able to get away with that 1/6 scaling. Basically, that's what comes out of treating the large molecules as large spheres. But as the chains get larger and larger, this scaling exponent becomes -1, which is Rouse. And so this is low density, long chains. And so the old-fashioned methods of transport properties based on Inskog methods are limited. And so that's a preliminary result at the moment, but I think it's going to hold up as time goes by. Another beauty of the simulation methods is we can actually identify the point at which the self-diffusivity starts to get much, much slower. So it's going down with the square of the molecular weight instead of just proportional to the molecular weight. And finally, when it comes to surface tension, the methods you've heard a lot about in the seminar series of using density gradient theory or density functional theory, those methods are essentially, if you've got the VLE right, they go right through the data points. And so I'll wrap it up then. I always talk too long, no matter what I do. So to summarize, we're seeing some definite improvements since Y2K. I think we can say demonstrably for certain properties that the more modern methods are, in fact, an improvement. And for quantum mechanical methods, that applies especially to the ideal gas properties. And for the transport properties and vapor pressure, I think the EMD methods are superior. We still have some work to do when it comes to the VLE, and I'm expecting LLE and solid liquid equilibrium to be similar to VLE, if not more difficult for the modern methods to compete with. So I'll leave it at there. I'll mention that we will be having open source Fortran codes available for PC-SAFT and all of my models, and also for the PR Lorraine model, which includes the quadratic mixing rules and their Huron-Vidal mixing rules. So stay tuned to the website there if you're looking for links to those kinds of resources. So thanks for your attention, and I'll be happy to answer any questions.
Thank you so much, Professor Elliott. It is really a pleasure to have you here with us again and with another marvelous presentation. We are now open to questions. If you want to ask one, you can raise your hand using one of the Zoom tools, or you can also write questions on the chat. And I would like to remind our YouTube viewers that they can also ask questions by writing in the chat. Bruno Horta wants to be the first. You can go ahead.
Hi, Richard. Very nice talk. I have a few points of curiosity. So about the data, we had a discussion, I think it was last year, about the difficulty to get new data nowadays because people are not dedicating so much time for data measurement, measuring data. And the amount of available data is more or less stationary, I would say. I don't know if you agree with that, but we had this conversation at some point. I don't remember the talk, but my curiosity is like, let's say that this data that you are using from NIST and from the other source, this is like a domesticated data because it's all systematically sorted and it's all gathered and cleaned, all that. How much of data you imagine, this is just for sake of curiosity, is in the wild, like in labs out there or in publications that were not taken into account for building those databases? Do you have any idea?
Okay, so yeah, let me talk a little more. And so really this, I'm speaking on behalf of my friends at TRC. And so I hope I don't misrepresent anything here. What they would say, and I've seen them show graphs about there is more and more data every year. And the amount of data generated is I think it's increasing exponentially. I think it's not, as huge an exponent as it used to be, but it's still an exponent greater than 1. So that might be surprising, but think about this. Ionic liquids. All the properties have to be measured again, right? And so there are some weird compounds with sulfur in them have vapor pressures being collected at something like 1 microtorr. Okay, so they're not the kinds of properties that you and I think of as being, exactly what we need. But they're properties being measured like that. And so within the scope of NIST's mission, they have to try and gather all of that data ideally. Now, because that's such an impossible task, what they really do is they have about 6 journals that they watch 100%. And they bring in a small army of undergraduates and high school students each summer to read all those papers and just type in the data. And so that's sort of how they operate. And by focusing on those 6 journals, they do a pretty good job for those 6 journals. And then they try to capture the data from the other journals. Now, we can get some sense of how broad that scope is by comparing what they get for some pure compounds to what DIPR gets for the same compounds. And so I've looked at some of those kinds of data, and I would say that NIST is probably getting 80 to 90% of the time has already captured the same data that DIPR has. So how much data is in the wild that is not captured by the TRC? For the compounds that DIPR has looked at, so that's a select list of compounds that are of interest to industry, 2,300 compounds. NIST is capturing about 80 to 90% of it. For the other 30,000 compounds that are in the TRC database, it's not 80 to 90. It's probably, I'm going to throw just 50 plus or minus 20. It would be a wild guess.
Thanks, Richard. We also have to take into account there that not all the properties are measured for all the compounds, right? So,
right. So NIST is only going to tabulate whatever's been measured.
Yeah. Thanks, Richard. Very nice.
Rafael Pellegrini wants to go now. You can go ahead.
Thank you. Thank you, Richard, for the very nice overview of these properties. My question is just out of curiosity, very simple. When you compare the vapor pressures, usually this comparison is very sensitive to how close you go to the critical point. And in your comparison, how close are the models going to the critical point, like 90%,
90%.
critical temperature, or what?
0.9, yes, exactly 90% of the critical temperature. And there are some limitations that deserve to be in this Joubert method, okay? So this is that translated consistent Ping-Robinson method, he calls it. He limits his vapor pressure coverage to 0.1 bars, 0.01 megapascals. Anything lower than that is outside the range of his analysis. And those lower vapor pressures tend to be where the larger errors are, because it deviates from straight line behavior more relative to the upper part of the the higher temperature part of that log vapor pressure versus 1/T. And so that's another way in which this comparison is not quite fair, because he's limiting his vapor pressures on the low end to the ones that work well. Whereas in the SpeedMD method and the ESD method, I limit it to 0.4 reduced temperature. So it goes from 0.4 to 0.9. Below 0.4, the ESD is just out of bounds, okay? The SpeedMD method goes down to 3 zeros and a 1, 0.001 megapascals. That's my cutoff for the vapor pressures. I arrived at that cutoff because I was just seeing so much scatter in the behavior and the trends of the molecules with the transferable force fields that it just didn't make sense that this compound would be off by positive 50% and that compound would be off by negative 50% with the same transferable force field, and they were fine if you were above 3 zeros and a 1. Okay, so I think the data in those really low vapor pressure regions might be a little more scattered. And so I just decided I'm just not going to go there. PC SAFT, I think, is similar to SpeedMD in that limitation.
We are using the range of 50% to 90% in our comparisons. I was just wanting to check if that's in agreement. Apparently, it's in agreement about the same you're using.
I would put you to go to 0.4. Yeah, I would urge you to go to 0.4.
Okay.
Bruno Horta wants to ask another question. You can go ahead.
Yeah, so Richard, when you mentioned about the Joubert database, that you said that this was a database that no one was using to train models for that database because it was a new database, right?
Right,
so,
right.
So you used it for comparing the other models. And my question is along this line. So about the generalization capacity of those models, right? So ideally, you would have to consider which was the training data for each of these models, and then to try to test or validate this model in a context where they were not introduced before, right?
Ideally.
That's something you tried to do with the Joubert database, right?
Actually, all of the methods here, I probably should have spent some more time talking about this. These are characterizations where we are optimizing the parameters in the equations of state for this exact database. We're not attempting to predict the binary interaction parameters.
Okay. But when you compare methods that have been trained on different data sets, it's difficult to evaluate the generalization capacity of the methods, right? So, because in principle, you're interested in using these methods to estimate properties that have not been measured before.
Right. So I've done a little bit of that when it comes to vapor pressure. And so, yeah. If you look back, there's a paper around 2008, I think it was, where we looked at this transferable force field with SpeedMD, and we separated the database into a training set and a validation set. And it was about either 2/3 training, 1/3 validation, or 50-50. I think it was more like 2/3 and 1/3. And so what we saw is the vapor pressure deviations when we did it that way for the validation set were maybe about 50% higher. And so it's true that predicting is harder than correlating. I think that's what you mean. Is that right?
Yeah, that's what, and that is also connected to a point that I think you didn't mention, but about the usage of machine learning models for predicting properties. I don't know if this will be a trend in this field.
Say again?
The use of machine learning models.
Oh, yeah. Okay. I've seen a recent presentation on that. It was applied to boiling temperatures in particular, and they were able to get about half as much deviation in boiling temperature as the best methods. Let's see. Yeah, so for boiling temperature, whereas the best methods here are around 3% deviation, he was getting about 1.5% deviation. But he had 30,000 parameters in his in his correlation, and there were only like 3,000 data in there. So he had 10 times more parameters than he had data. So I found that confusing, but that's the nature of these machine learning methods. and he did separate his database into a training set and a validation set. And the increase was, instead of 1.5% deviation, maybe he got 1.9% deviation. It was still significantly lower than what I was able to do with these group contribution methods. And these group contribution methods have on the order of 75 parameters in them to characterize all the different groups in the molecules.
Yeah, interesting. It's a black box approach, but interesting for prediction power.
Right. I don't fully understand it yet, but they do the right thing in terms of separating the training set and the validation set.
I guess no one understands because it's really brute force learning procedure, and we don't know what's in the black box. It's quite hard to try to get the reasons for such predictive power from the black box.
And it's an opportunity. I think maybe I'm mixing up all the different seminars, but I think Carlos Vega might have mentioned this too, or it was part of the conversation later, that when you use these machine learning methods, you can do better if you have to make some sort of an assumption about your correlation form. And so in the context with the discussion with Carlos Vega, what I was trying to say is, if you start off with your primitive force field, something like a Wertheim's model, and you sort of subtract that out of the basis set of all the different descriptors, okay? And you make sure that the physics of that short range types of interactions is characterized first, and then use the machine learning as a kind of a blank canvas, okay, to color in the details of this. Think of it as like a coloring book, right? You've got, a picture of a cow, and now it's just a drawing of a cow, and now you're going to color in the cow. So I see the machine learning as more of the coloring details part, and the physics is something that you should put in as the sketch of the basic, what does a cow look like? And so when I was talking with this guy who developed this method for boiling temperatures, he had just assumed that boiling temperature would be linear with respect to the number of descriptors. And so basically linear with respect to molecular weight. And so I said, well, if you were just to turn it around and assume that 1 over the boiling temperature was linear with respect to 1 over the molecular weight, the data we have seems to indicate you would probably get a better correlation, especially for heavy compounds. And he was having a problem with heavy compounds. And so he said, oh, I can do that. And so that's a simple example of how, just thinking about what it ought to do, the physics of it first, and then putting your machine learning on top of that, I think is the right way to go.
Yeah, I think so too. Thanks, Richard.
Let's see, we have something in the chat.
Yes, we have a question in the chat. I don't know if he wants to speak. Jordan, are you there?
John O'Connell is here, so he can ask. I think it's better. John, you can ask directly.
It looks like he's just posted a comment, actually.
That's right. I only wanted to say bravo. You're doing wonderfully well, and I wish you. I hope that you are able to complete it, Richard. I can only say that 20 years ago, when we published the 5th edition, we were approached by McGraw-Hill to say, well, do you want to do the 6th? And Poling and Prausens and I shrunk back in horror and said, no way. So good for you. Yeah.
We had a previous question. I think I'll read it because I don't know if Eugene is here. So he says, thank you very much for your presentation, Professor. My question is the following. For mixtures with high hydrogen and polar interactions like ionic liquids, is the prediction of boiling temperature by group contribution method good or bad in relation to other methods as molecular dynamics?
Okay, so boiling temperature, we didn't have a lot of data to go by. And what we had was this trap UA force field, and it's roughly 5% deviation, which is similar to some of the not very good methods. Okay, and so boiling temperature, I would say it's not good molecular dynamics yet. We can't demonstrate that, but boiling temperature and vapor pressure are very similar. And so after the fact, it occurred to me that what I should be doing actually, and I don't know if I'm going to have time this time around. I should be able to take the SpeedMD method and turn it around and just calculate the vapor pressure, calculate the temperature at
Right.
1 bar of pressure, and that will be the prediction of the boiling temperature. That, just use the transferable force field for that, and I'm done. And I didn't do that. And another part of the problem is, if you look at the database, we've only got about 480 compounds here in the database that we're comparing equations of state with. Whereas with the boiling temperature comparisons, we've got 4,000 compounds. Okay, so I could have another row here that said SpeedMD, but the number of compounds per row would be 250 here, 20 here, small numbers. And the deviations, though, I expect would be probably similar, if not a little bit better than this EMB method. Okay, and so I would say I should do that. If some people are asking about it, I better go do it. It's not going to be too dramatic, but it's going to be let's say 2.5% error, probably across the board, and but for small numbers of molecules, and so that's what the SpeedMD method would give, I think, and that includes. So the question was, well, what about when you make the molecules complicated? Okay, so polar molecules include things like nitrates and esters and acids. Well, I think acids are in the association category. We do not include anything about ionic liquids. I'm not sure that there's a lot of vapor pressure data available for the ionic liquids, and what data are out there are sometimes controversial because of the presence of water, and so I don't think we're quite ready to put ionic liquids into this particular database. I hope that answers the question.
Okay, now Professor Fred, you can go ahead.
First of all, I'd like to congratulate you for this huge work. I think it's going to be very interesting, this book. Well, this book is interesting for a long time ago, always new version. I think it's very nice to see, and it's a lot of work in it. So I congratulate you, John, for the 5th version. But it's a lot of, well, congratulations. that's all I can say. But I'd like to hear about you about entropy scaling to calculate transport properties.
So I looked at that. Actually, I think I might have a slide open here if I can switch from PowerPoint to
it looks to me that if you have a good PVT correlation or PVT data, you can get very nice viscosity, diffusivity, conductivity. I think it's very interesting method. I'm not okay. Did you present this?
No.
No. Okay. Okay. So.
So as I was putting my slides together, I went back to some old papers to cut and paste some pictures of
Okay.
the diffusivity properties. And so this is actually a couple of graphs that are in the paper from Garrick and Elliott in 2010. And so what we did was we said, now we've got this data on the viscosity, the simulations of the diffusivity, self-diffusivity, and a molecular simulation of a self-diffusivity is pretty reliable. It's very fun, very basic, right? And so if it's true that this entropy scaling applies, that the self-diffusivity is somehow just connected with the deviation of the entropy from the ideal gas property, then it ought to be transferable from one chain molecule to another. And so we had really good data for that. So we made the comparison. And if that was true, then this would be all one curve. And it's not. And I said, well, what if we were to put it instead of on just an entropy per mole basis, let's put it on an entropy per volume basis. It works a little bit better for the longer molecules, but not so well for the shorter molecules. So there might be something like that, some kind of asymptote being approached. But the C16 is actually on the left side of the C30. So I'm not sure if that's really valid either. So after I presented this at an AICHE meeting, and then Tom Truscott, who is still a pretty big advocate of the entropy scaling method, we had some discussion, and he said, well, it's not really supposed to go transferable from one molecule to another. It's only supposed to describe the scaling of a molecule with respect to itself. And I said, okay, well, we would have that's going to come out of the correlation with respect to the attractive effects. And do I have a slide on that? We're digging through some old slides here. So here, this slide actually was showing how the self-diffusivity changes as you apply the attractive forces. And you see there's this kind of consistent slower diffusivity as you add attraction. And that's reflected in the experimental data as well as the simulation data. And so when you look at what's the temperature dependency of that, it turns out that the first order contribution in temperature is really small and maybe arguably negligible. And I had a discussion with my grad student about this, and she said, I think it's zero. There's no reason to put it in there. And I said, yeah, but you can't have a second order term without the first order term. And so that was the way the discussion went. I regret it now, because what turned out was, if you look at the residual entropy in a perturbation theory, okay, what is the Helmholtz energy, right? It's A naught plus A1 over T plus A2 over T squared dot, dot, dot. Well, what's the internal energy, especially in the speed MD model? Because there is no U naught. There's no energy of molecules overlapping. They cannot overlap. It's a rigid model in the high temperature limit. And so U minus U ideal gas is equal to U1 plus 2 times U2, 2 times A2 over T squared, dot, dot, dot. Well, to get the entropy, you've got to basically subtract the Helmholtz energy from the internal energy. That cancels the U1 term, and you only end up with A2 over T squared. And so the entropy departure function goes, its first term in that series is A2 over T squared, which so happens to be the same temperature dependence that we see in the viscosity or the diffusivity correlation with respect to attractive forces. So does that mean that there's some maybe metaphysical connection between entropy and diffusivity? Or is it just a coincidence that they both seem to have that same temperature dependency, that the first important term in the temperature dependency goes as T squared? That's where I'm at with it. But I will add this, my friend at NIST, his name is Ian Bell. He has a fair number of papers about this entropy scaling method applied to his the RefProp database. Ian and Eric Lemon are essentially, you put them together and you've got RefProp. That they're the principles of the RefProp correlation, which is then the chemistry web book. So he's a big believer. One caveat I'll add to that, he's almost always looking at fairly small molecules. And for spherical molecules, okay, sure. But then we come back to the chains, and whatever I've looked at, as the chains get bigger, things kind of fall apart. So it's a work in progress, and I can't give you a definitive answer, but those are my impressions.
Thank you. I'm also talk with the same guy in this, and I think maybe you're right, but we tested scaling with Helmholtz scaling instead of entropy scaling. But instead of ideal gas reference for viscosity, we prefer to use hard spheres reference. So the scaling is compared with hard sphere instead of compared to the limit of ideal gas. At least for viscosity, it works very well. But okay, we are still in progress.
Yeah, I would urge you to get away from the spherical reference, that NSCOG reference, because and look at longer chains of things, because that's really where you start to see the discrepancies from that sphere type scaling of transport properties.
Okay, thank you.
Does anyone have another question? I don't think so. So I think it's time to wrap it up. Thank you again, Professor Richard, for another presentation.